Next slide. We can use the spectrum from an object to determine its speed and direction of motion. With the Doppler effect, the motion of an object towards you or away from you produces a shift in the wavelengths of electromagnetic radiation we see. Now, the object itself is producing the original same wavelengths, but what we see is shifted because the object is moving relative to us. The wave crests are closer together if the object is moving towards us, so we say the spectrum is blue shifted. The wave crests are farther apart if the object is moving away from us, so we say the spectrum is red shifted. The Doppler effect tells us only about the radial motion, that is, the motion directly towards us or directly away from us. The direction of the Doppler shift, blue shift or red shift, indicates if an object is moving toward or away from you, and the amount of the shift tells you the speed. A greater shift of the wavelength means the object has greater speed. It's much easier to measure shifts in the absorption line or emission line pattern. With a blue shift, the pattern is shifted toward shorter wavelengths, and with a red shift, the pattern is shifted toward longer wavelengths. The Doppler effect works for any type of wave, including any kind of light wave, whether it's gamma rays, visible optical light, or radio waves. With a radar gun, the device produces a radio wave of a certain specific wavelength. If it bounces off your car while you're approaching the device, the reflected waves will be scrunched up. The radar gun measures the wavelength of the reflected wave and calculates the speed from how much the reflected wave is scrunched up. If the reflected radio waves are scrunched up too much, you get a ticket. If you're moving away from the device, the reflected waves will be stretched out. If they're stretched out too much, you get a ticket. The bottom two graphs show why it is much easier to measure Doppler shifts with absorption lines or emission lines than with looking for changes in the overall color. With the thermal continuous spectrum, one color shifts into another, so you won't be able to see any change in the object's overall color unless it is moving extremely fast, such as 1/10 the speed of light or faster. No star in our galaxy moves fast enough to change its overall color enough for us to detect. We have to use spectral lines. With spectral lines, we're able to measure speeds as slow as a leisurely walking pace.